what we call how the electrons are hanging out, because I want to talk about that. So first off, if I were to ask you, I have a periodic table, so I'm going to grab my periodic table. If I were to ask you which is more similar to germanium, germanium's 32 here, which is closer to germanium with regard to how it behaves, would you tell me how many people take arsenic or silicon? How many people think arsenic's more like germanium? How many people think silicon's more like germanium? Well, how many people think neither one's like germanium? Okay. Well, so here's the deal. It's kind of like days of the week. Remember, we could call this Friday. Okay, today's Friday. And so in that sense, silicon, like a week earlier, is more like germanium than Saturday is like germanium. Okay? So the answer is actually silicon. So we have this kind of similarity going. We call these groups or families. It starts with letter P. What do we call these? Those across. Periods. Yes, those are periods. Very good. Where are the metals on this? Left or right? Left. Yep, metals are left. I know I get left and right. So again, how can we tell the metals and the non-metals? I call it the jag. And I kind of had you guys, and in fact I have one I marked up where I take boron, I do a line, and it kind of goes over and over and over and over. It's the jag that separates the metals from the non-metals. Perfect. Yep. So I want to pick up, this slide talks a little bit about something called valence electrons. So first off, and I didn't butcher this part. So why do I have, let's pick on carbon, why is there +6 there? Protons, yep. Carbon has 6 protons. And what are the 2 and the 4 here representing? Electrons, exactly. So you have 6 and 6, perfect. So where's germanium, silicon? Okay, so actually if we were to have germanium down here, we would see that it, with regard to electrons, would also have 4 valence electrons. I'm going to circle this 1 here, these 2's here, these 3's here. What those numbers there I'm circling are representing the valence electrons. They're the outermost electrons. So how many valence electrons does chlorine have? Here's chlorine. How many valence electrons does it have? 7. 6. And there's this cool little pattern. 7, yes, 6. So one of the things, and different periodic tables do it differently, but remember where I said that we're going to go ahead and take these 2 columns, these 2 families, and they are 1A, 2A, and then we have to skip these. What are these? These transitions, both great, yep. These are transitions, perfect. And then we go over here to 3A, 4A, 5A, 6A, 7A, and 8A. Now, for the A's at least, all we got to do, it's pretty slick, is if we go pick on chlorine, you told me 7 valence electrons, all we got to do is look at the group number to know how many valence electrons there are. Does that work for all of them? Aluminum. 3A, 3 valence electrons. Okay? I think that's a wonderful thing. But it only works for the A group. For the B group, not so much. Okay? Cool. Well, I don't think I'm going to need this one now, but all I did was I went ahead and pulled in that one figure. If we focus on 1A, you can see the 1 valence electron. 2A, 2 valence electron. What's under magnesium on the periodic table? Potassium? Calcium, thank you, calcium. So calcium would have a 2 out here also. Now, I think what threw me off the other day was that, these are where our group B goes in, inserts. So basically the periodic table divides with 2 columns here, and there's actually 10 columns here of B's, and then we have 6 columns over here. So anyway, all right. Group 4A, carbon and silicon, 4 valence electrons. Group 5A, 5 valence electrons, 6A, 6 valence electrons, 7A, 7 valence electrons. Now, I'm going to emphasize, so how many valence electrons over here in this last column? 8, perfect. I know this guy is kind of an exception, you know, but otherwise it's going to be 8, 8, 8, 8, 8, 8 going down. What is the name of this group of elements? Do you guys remember? This 8A. Noble gases, perfect, yep. These guys are noble gases. They're sometimes, they're also called rare gases because they're so rare. And sometimes they're called inert gases. What does inert mean? Like if you have a medicine and you have an inert ingredient, that means it's inert versus active. What do you think an inert ingredient would do? What do you think an active ingredient would do? Explode. Explode, active, reacts. How about a medicine? Active ingredient. It's going to get you better. That's my general point. Active ingredient, it's going to get you better. Inert ingredient, it's just along with the ride. So they call them inert gases because actually they don't like to explode. Inert gases, they are so like chillaxed. They don't want to react with anything. They're very unreactive. Very unreactive. They're your inert ingredient in your. Bless you. So now we're going to go around the room and we'll start the back of the room this time. So Ashley, find sodium on your, and we're going to go around, so everybody get ready. Ashley, find sodium on your periodic table, and do you think sodium is a metal or non-metal? It is a metal. We're good with that? So put M for metal. Okay, Ian.
I don't have my.
You didn't bring your packet thingy? Oh, your periodic table?
Yeah.
Ian, find carbon, and is that a metal or a non-metal? It is a non-metal. Carbon's a non-metal. Perfect. So let's go with you, Jasmine. So I'll put NM for non-metal. How about, what is the group number for chlorine? The group number. Oh, yeah, it would be 17. What's the A designation? Ah, it's 17, so she's right. I'm right, 17, and the other name is 7A. Yep, very good. 17 or 7A. Perfect. 17/7A. Okay, Nadira, what is the period for potassium? What period is potassium in? 4. I buy that. Period 4. Perfect. Okay, Mackenzie. Give an example of a noble gas. Neon. Neon, good choice. Excellent. Okay, Hannah. Give an example of a halogen. What do you think? Take your time. It's going to be kind of on the right side of your chair. No, it's next. Oh, bitter. Oh. What's your choice? Chlorine. Chlorine. Very good. Yep. Very good. That's 7A elements, halogens. All right, Kate. What about which element? Oh, this one narrows it down. It's like kind of like a grid sort of thing. It needs to be group 2A, period 5. Strontium? SR? Okay, very good. Perfect. Yay. Okay, so back to you again, Ashley. Which element is found, again, it narrows it down to group A, period 3. Silver? Sulfur, excuse me. My hearing is just terrible. Sulfur, S. Perfect. Okay. Then we're back over to you, Ian. How many valence electrons does a boron atom have? But I don't know, I mean, you might want to use, does that one have the A's and such on it? Yep. So he's going with 3, me too. Yep. So that's why, to me, I like not just the new designation of group 13, but group 13 is totally correct. But it's 13 and it's also 3A. So we just learned it must have 3 valence electrons. Perfect. Very good. Okay, Jasmine, how many valence electrons does a barium atom have? The joke is, what do we do with dead people? Barium. I know, it's terrible. I'm sorry. Barium. So you're gonna want to use the A designation and not off. So we put it. So barium is right here. So 2. Yeah, this is a 2. Perfect. She's going with 2. Me too. Okay, Nadira. She's going with 4 valence electrons because it is 4A. I'm liking it. Very good. Okay, Mackenzie, how many valence electrons does xenon have?
8.
8. Dun, 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 because it's 8A. I'm liking 8 valence electrons. Perfect. Okay, I think that's it for now, although we'll pick up with Hannah when we come back to some more questions. Pie chart time. So of all these lovely elements, this is the distribution of elements in the universe. Now this is not by weight, but this is total atoms. So what do you think? A lot of hydrogen in the universe, followed by helium, and then all others. So we're a carbon-based life form. Of course, we have carbon, aluminum, iron. You know, we have a lot of things on here. I liked what I think Carl Sagan's video pointed out, that actually it kind of goes every 2s. So for instance, if it's an even number of protons, that's more likely to be abundant. So it's kind of fun if you just kind of look across, you're like, well, that means we have less potassium and more calcium, okay? So anyway, that's kind of neat. And there's a reason for that. It has to do with the stars, how it's made. So this one is the Earth's crust. So what's the most abundant element in Earth's crust? Oxygen. What's the second most abundant? This is first. What's second? I'm liking silicon. How about third? Aluminum. Yep. So that's the Earth's crust. Now this one creeps me out. It really does. You know, you think of body snatchers, right? So in the human body, if we were to take all of the compounds that make us up and distill it into a pile of that element, a pile of that element, a pile of that element, this is what we look like. We're much more precious than this pile of elements. Now, the reason that we have a lot of oxygen, and this is by mass, by the way, so not by counted number of particles like the universe one was. So we have a lot of oxygen and a fair bit of hydrogen, considering how hydrogen is so light. Why do you think we have a lot of oxygen and hydrogen? Because we have a lot of what compound in our bodies? Water. Yep, we have a lot of H2O, and that kind of is a little bit white, what's represented here. Okay, so this assignment will be due when we meet again on Monday. And we're not done, we have to keep going. So it's tempting, but speaking of though, and so how does this work? I don't want to get everybody's weeks mixed up. But we meet next Friday, but we don't meet the following Friday. If you look at the 4 dates I gave you, yeah. So in 2 weeks, don't ever come next Friday, or get in trouble.
Today's the 9th,
The 9th, okay,
Then you
the
have
7th would be
16.
16.
so we don't meet on the 23rd,
Yes, ma'am.
all right?
And actually, it's like if you ever had a teacher out, you know, K through 12 or whatever, they had in-service days. We have in-service days. We call them professional development days. And if you've ever heard teachers complain about them, I know I'm recording, but nobody listens to my recordings anyway. It's like, you know, you're like, I'd rather be teaching, right? But anyway, so no classes Friday. 2 weeks though.
I listen to your.
Oh, no. Well, don't quote me on that one. Right? So I feel like we already kind of talked about this, but we're gonna hit it again. It feels like deja vu to me. An atom, okay, it's got 3 pieces to it, and we're gonna talk about those 3 pieces again on this slide. I think the reason I wanted to bring it back is because now we're gonna talk a little bit more in depth how an atom can vary in the number of those particles. So, an atom, of course, we have the nucleus with the neutrons and the protons, and outside we have the electrons. Electrons are negatively charged, essentially massless, which probably drives physicists crazy. That's what chemists talk say, that they have no mass. And they swarm in a cloud. You can't really, it's Heisenberg's uncertainty principle says you can't really know, they don't orbit like the planets orbit the sun. Oh my gosh, though, I did some more looking into that, that Elon Musk thing, the SpaceX, and it's just amazing. So, bless his heart, or the scientist's heart, they shot off of, if this is the Earth, okay, they escaped Earth's gravity, and and we know Newton's laws of motion say, dude, once you get out, there's no particles. If you have a certain trajectory, it's gonna keep moving in the same direction with the same velocity unless occupied by an outside force. So that outside force, it is tethered to the sun in the sense that it's not gonna leave our solar system. So we have the whole gravity thing going on. But my point was going to be that after it got to a certain stage, the payload part, it separated, and literally the vehicle I talked about the other day, the Tesla, beautiful red vehicle, was ejected, or not ejected, but just sent on its way to orbit the sun. So there's just like a naked Tesla vehicle up there with a dummy mannequin driving it. On the back it says "Made on Earth." Okay, and the whole recording, this kind of surprised me. Recording of the David Bowie song, it only lasted for like 3 hours. Can you get a battery? I could get a battery that would play along with that. But anyway, that's okay. So anyway, so now it's quietly. They wanted to insert it in a closer orbit, but now it's going to go through the asteroid belt. I know. But the thing about the asteroid belt, we'll talk about this, is that the little crumblies that make the asteroid belt, they aren't close together. So there's not a very good chance it's going to run into anything. I wonder how the insurance works on that vehicle. So anyway, I don't know how I got there. Oh yeah, because I was talking about, so electrons don't orbit the nucleus, but they're in a cloud outside the nucleus. Protons, positively charged, they weigh about 1 AMU. And your textbook uses U. And sometimes I will actually use AMUs. So you'll have to kind of bear with me. Now, the reason they had to come up with a new mass unit was you can't weigh atoms in grams or kilograms or pounds or ounces. You need something much lighter. So if you were to take a gram, okay, of mass, it's actually equal to 6.022 times 10 to the 23rd AMUs. So that's amazing. Protons are very important. We call them the atomic number, right? So the whole number that's in the box for an element, that's its atomic number, protons. All right, then the last one is neutrons. Okay, we're going to pick on neutrons here in a minute. Neutrons actually have a similar mass to protons, and it's because the neutrons are there, and I think Carl Sagan kind of talked about the hooks. The neutrons help kind of make the protons coexist. Otherwise, positively charged protons would want to separate. Okay, very good. So there is this phenomenon with atoms of a given element. Now, to be a given element, they have to have the same number of protons. but I kind of call it Mother Nature's spice. You know how you add a little bit of salt, add a little bit of pepper. It's the number of neutrons, actually, in the atom or the nucleus of the element that can vary. So the number of neutrons can vary. They have the same element. When that happens, we call those isotopes of the same element. Okay? So isotopes of the same element. And I'm going to take you out to one of my favorite online periodic tables. It's an interactive periodic table, so you can click on carbon and know more about carbon, for example. Now, not all elements have different isotopes, or multiple forms. So, but whenever you hear the word isotope, just be thinking same number of protons, different number of neutrons. Right? I think we talked about mass number. It's being brought up again. Remember the mass number, and it drives me nuts. Mass number is the symbol A, I think. Mass number is A. And that is the number of protons, which has to be set in stone for it to be a certain element, plus the number of neutrons. And the symbol for neutrons would be N with a little superscript 0. So that's what the mass number is. So we're going to do some kind of little ciphering, but do you see where the mass number will differ for different isotopes because we are adding or subtracting our neutrons? So I'll kind of show you what that looks like. So uranium, of course, is, I don't know how I feel about nuclear power. But uranium can be used, it's a big old honkin' element. Let's find uranium on here. How many protons does uranium atom have? It does have 92, yep. Uranium has 92 protons, okay? So it's big honkin'. Now, the thing about big atoms like that is sometimes they will kind of naturally, or without a whole lot of effort, go ahead and splitting the atom. You heard of splitting the atom. Okay, that's called nuclear fission, break. Okay, so one isotopic form of uranium is just normal. It's stable. It doesn't like to do nuclear fission. Another form of uranium, and I think it might be the 238. It likes to react with regard to breaking apart and releasing a lot of energy to either power a plant or to honestly have a bomb. Okay, yeah. So there's your bullet. Okay, so some of these are more stable than others. Which one of these, 235 or 238? By the way, these are the mass numbers. So each of these reflect the number of protons plus the number of neutrons. Let's go ahead and see what that means. You guys told me 92? Okay. Now, I'm going to take my calculator out because, quite frankly, I don't know much of it. But what, for instance, in this version, this isotope of uranium-235, if it has 92 protons, and the protons plus the neutrons is 235, what's the neutrons? What do you think? What'd you get? Me too. We got 143 neutrons. How'd you do it? Yep. You took 235 minus 92. Perfect. How about this uranium? U-238. What'd you get? I guess it would be just, what, 3 more? Does that make sense? 3 more? Yep, 146. Perfect. 146 neutrons. And so We got that by taking the 238 and from that subtracting the 92. Perfect. So here's that interactive, if you want to jot down where I'm going to take you, but I did go ahead and put this also, it's in Canvas, so www.ptable.com. Maybe. So you see that, I know it's Wikipedia, but you know, some things Wikipedia can't get wrong. The thing about Wikipedia is, especially if it's a hot topic, there are people continually reviewing it and saying if they get it totally butched, then, so I have a story to tell about Wikipedia. So years ago when I first started teaching weather, meteorology, I am fascinated with hurricanes and how the hurricane season unfolds. I just am fascinated. So I was just Googling, and I said, well, what about the current hurricane season? And so I was just clicking on links, and I didn't pay attention. It took me to a Wikipedia site for the current hurricane season. I was like, wow, that's amazing. And then I went to come like, wait a minute, that hurricane hasn't happened this year. So anyway, I don't know what it was, but Wikipedia got on a good thing I didn't like show my students. I'm like, wow, look at this crazy hurricane season. Because you know they name hurricanes, and it's just very exciting. So anyway, so you see across the top, properties, orbitals, isotopes, compounds. I'm going to go ahead and go with isotopes. So if I click here, then I can go ahead and click on, for instance, aluminum. Now you see where aluminum, it gave me 3 boxes. Okay, so I can click on one of the boxes. Oops, come back. There's 2 boxes, I guess, sorry. We have one mass number 26, and then you have some information up there. The half-life is interesting, so in that many years, half of it will go away. Notice the abundance. Is it very abundant? Yeah. Well, I hope the other one's very abundant. So let me click on isotope 27. Wow. So 100% abundance. So this guy is very out there. Aluminum 27, aluminum 26, not so much. Its half-life, by the way, if you were to use that half-life and compare it to the age of the Earth, actually it has all gone away, even if that aluminum 26 ever existed. It's all gone away, converted to something else, something small. That's what half-lives are. So speaking of half-lives, let's just go ahead and I'm going to pick on these guys down here. I'll ask this in the form of a question. Can we find these elements on Earth, like naturally occurring? No. These guys are man-made. Actually, anything above, I think uranium is man-made. So I'm going to show you what that looks like. So if I click on one of the isotopic forms, let's see what its half-life is. About 30 seconds. Okay. So this is the 270. It lasts 30 seconds. Well, let's get even crazier. Let's go to tennessine. And I need to click on the isotope. What's the prefix M stand for? The metric prefix. Milli. So 50 milliseconds. 50 milliseconds. That's half-life. That's adorable. If you're like me, you're like, what would you use that for? But I just think that's neat. So different isotopic forms. All right, so I'm going to make columns above here. Now you guys don't have this one. We have a place to put it, but so we're going to start with calcium that has a mass number of 40, and I'm going to put, and then I'm going to pick on people, starting with Hannah. So I'm going to put number of protons. And I'll go ahead and put number of electrons. Whoever gets that one, I think, it's got a little easier than the others. And then I'm going to put number of neutrons. And I'm going to put number of neutrons, how, that would be one person. And the fourth column is going, I know this is hard to read my writing. The fourth one is number of neutrons, just number of neutrons. It'll make more sense when we do one. Okay, so you'll need a periodic table. So Hannah, how many protons in a calcium atom? She's going with 20. Me too. Perfect, 20 protons. If it's neutral, and these are all going to be neutral then, Kate, how many electrons? Also 20. See what I mean? People who get that one get it easy. Okay, Ashley, I don't want you to tell me how many, but I'm trying to say this is how. So how would you go about calculating the neutrons with this given information? The calcium 40, 20 protons. Just tell me the subtraction you would do to calculate neutrons. So remember, this is the mass number. So this is number of protons plus neutrons. If this is protons plus neutrons, and here's protons, how are we going to get neutrons? That's what I would do, 40 minus the 20. And then back to you, Ian. So how many protons does that give us? Sorry, neutrons. It gives us 20. Perfect. Very good. Up to you, Miss Jasmine. We're picking on now, still calcium. How many protons? It's not a trick question. It is 20. It is 20. 20 protons. It stayed the same. Nadira, how many electrons if it's neutral? 20? Very good. Mackenzie, how are we going to calculate neutrons?
44.
Very good. And I don't know if you need a calculator, Hannah, but so how many neutrons do we have? 24. Perfect. Yay. Awesome. So back to you, Kate. So we're dealing with KR. I'll ask you a couple questions then. What does KR stand for, Kate? It does stand for krypton. Very good. And so how many protons are we talking?
36.
36 protons. And then Ashley, if it's neutral, how many electrons? 36 electrons. Very good. So Ian, how would we go about calculating neutrons? You would subtract 36 from 84. So 84 minus 36. And feel free to use a calculator, Jasmine, because I probably would. What do you think? 34? Perfect. Thank you, ma'am. All right. Nadira. 2 questions again, kind of like I asked Kate. So SN, what's the name of that one? Starts with T. Keep looking, you'll find it.
Oh, 10.
10, perfect. And how many protons are we talking?
50.
Very good. I couldn't hear. My hearing is just terrible. Okay, 50, good. And so if it's neutral, then Mackenzie, how many electrons?
50.
Also 50. Very good. So Hannah, how are we going to go about calculating neutrons? 120 minus 50. And then Kate, what would that, how many neutrons we got? I'm going with 70. Perfect. Okay, 2 questions, and back to you, Ashley. What W stands for what element? And then how many protons? It is tungsten, one of my favorite. Yeah, and I think the joke tungsten goes something like, what happens when you get your, when a bee stings you in the mouth? You get your tongue stung. Okay, how many protons? How many? I'm sorry. 74, perfect. Very good. So Ian, if it's neutral, how many electrons? Also 74, perfect. Jasmine, how would we go about calculating the number of neutrons?
180 minus 70.
That's how I do it too. So feel free to use the calculator, Nadira. How many neutrons are we talking?
110.
110. Perfect. All right, last but not least, how many protons do we have for this atom? Mackenzie. 74. It's the same element. Very good. If it's neutral, how many electrons, Hannah? Also 74. Kate, how are we going to go about knocking out the number of neutrons?
182 minus 70.
Yep, 182 minus 74. Very good. And so, Ashley, how many protons are we talking? Or, excuse me, how many neutrons are we talking? 108. Perfect. So we aren't gonna, like, we're not, it's not time to leave yet or anything, but we aren't gonna finish this whole packet, I don't think. But you have some questions kind of like this in their last slide. So my point is that if you were looking for something to do this weekend, you could work on those. I don't know, maybe we will get through. I'd be surprised, but we'll see. Okay, so I'm switching gears here, but just to re-solidify what we just talked about, if we talk about isotopes, which of the three particles that make an atom is changing with isotopes? That's what it is. Neutron, yep, neutrons are changing with isotopes. Neutrons are changing. Now, I'm switching gears, because now I'm going to talk about what's that particle in the outside of an atom? Electrons. Yeah. Now I want to talk about how electrons, if they vary, what does that look like? Because just a minute ago we kept saying that the atom was neutral. The atom's neutral. What's the relationship between protons and electrons? They're the same. I'm switching it up here. That's not always the case. So the cool thing about it is that the little pluses, positive charges that the protons bring is the same magnitude or the same strength as the negative charge that the electrons bring. And that's kind of why we say you have equal numbers, it's neutral. Okay? Okay. Ions. Neutral atom will have the same number of electrons because it has protons. It's funny, and it actually dawned on me a few years ago, but to me it makes sense that protons, they're stuck in the middle of an atom. Your protons aren't going anywhere. Your electrons, on the other hand, okay, they can actually, we're going to see electrons can get kicked off. Now, if I kick off an electron, what will that mean about my ion? Does it seem like it will have more pluses than negatives, or more negatives than pluses if I kick off an electron? More pluses. So actually what we just taught, what we said, if you kick off an electron, you're going to end up with a positively charged ion. The other thing is we have our protons minding their own business, electrons minding their own business. They're equal. What happens if we bring in an electron or two? Now, do we have more protons or more electrons? Now we have more electrons, so it's going to be negatively charged. Those are our only two options. Kicking off electron becomes positive. Bringing in electron becomes negative. Those are your two options. So, metals. Where are the metals on the periodic table? They are over here. Yep. And actually, this is the one I drew in the JAG. So, this one. Project's prettier, but anyway, you might want to put a JAG here. So the metals tend to kick off electrons, 1 or 2 or 3. Okay. Well, guess what the nonmetals do then? They get electrons, exactly, become negatively charged. Yep. But before I go on, I want to underline a word here. Because ions come in two flavors. One that an electron is kicked off, what the metals do, we call that a cation. And it's cool because actually in the word cat, it's C-A-T, cat ion. I like that. I've never seen it, but anyway, cat ion. Not to be confused with occasion. I just think that's funny. But I can see why people will pronounce occasion. All right, cool. Well, the other one, it must be the nonmetals tend to pick up an electron or two or three, and what do we call them? Anions, yep. And I shouldn't have left y'all out there because sometimes it kind of looks like an onion, looks like the word onion, like an anion, but it's an anion. I would throw you off, but yes. So we have our metals tending to form pluses, cations. Our nonmetals tending to form, they pick up electrons and form anions. So this is a little insert. Now, what are these numbers here? These numbers, like I'm gonna circle 8. We'll put 8 here, 7, 6, 5, 4. What are those numbers? Valence electrons, exactly. And it's a little game. So the deal is, what's group 8A? What do we call them? They're the noble gases. You guys told me the noble gases, inert gases, rare gases. It's a little game. Actually, all the atoms want to try to be like these guys, like the group 8As. Okay. So does this make sense that actually, I'm going to pick on sodium because it's easier. What sodium will do is kick off this electron, this one right here, this guy, he'll kick it off, and in doing so, he will become a +1 charge. And I don't mean to make it too complicated, but when sodium does that, do you see where it has 11 protons, but now it has the same electrons in the same order as actually neon, which is in the period before it. So main group elements will lose or gain the number of electrons they need to get 8. So I picked on sodium here just a minute ago. Sodium is a 1A. Sodium and lithium and whatever's under lithium, they will all kick off that one electron and become a +1 charge. I'm going to go ahead and clear my slide because what I would do on this sheet, or a sheet that you bring with you on the test, is above column 1A, I would write a +1 charge. And the reason for that is that if it's going to do anything with regard to its electrons coming or going, it's going to leave 1 electron. So what I usually tell students is I go a +1 here. For 2A, I go a +2. For 3A, that means I got to skip the B's, right? For 3A, actually just beginning with aluminum, not boron, it gets a little complicated, but aluminum on down, I go a +3. So they kick them off, and we said that the metals pick up an electron or 2 or 3. So looking at fluorine and chlorine, how many valence electrons do they have? 7. Yep, they're 7A. So how many do they need to pick up to get 8? Well, just 1 electron. So that's why at the top of 7A, I would put a -1, because that's the anion charge they form. On top of 6A, I would put a -2 because they pick up 2 electrons. On top of 5A, I put a -3. And this is where sometimes students will go, well, what do you do with 4A? And I usually just leave them open because they can kind of do what they want to do. Oh, bless you. All right, so who did we stop with? Who gave me the last answer? Do you guys remember? Ashley? Okay, all right, Ian. Find sodium on the periodic table, so what charge does it form? Oh. I'm sorry, we're picking on you. Actually, they're already on paper, so it's +1. But are there any questions about that? It's 1A. It's gonna kick off its 1 valence electron. Okay, oxygen 6A, it's gonna pick up 2 electrons, a -2. Bromine 7A, it's gonna pick up 1 electron, -1. Magnesium 2A, it's gonna kick off 2 valence electrons, get a +2. Nitrogen 5A, pick up 3 valence electrons, be -3. Potassium 1A, kick off 1 valence electron, +1. Sulfur is under oxygen, so it's 6A, picks up 2 valence electrons, picks up 2 electrons, -2. Fluorine 7A, 1 electron, -1, picking it up. Calcium kicking off 2 electrons, +2. Phosphorus picking up 3 electrons, so it's a -3. So now do you get even a better sense of why actually kind of within the same group, the same column, the same family, they kind of behave similar? Well, that's a good place to stop. We don't have a whole lot to finish up, but we'll go ahead and do that on Monday. But like I said, if you're one of these that likes to do their homework, you should be able to kind of do some of that homework already.